clear up things that you can't figure out from your notes. Okay. And also the exams, you should know, aren't exercises in completing something in a finite amount of time. The exams are made up so that everybody finishes, and that's been the pattern. I didn't encounter any students last year who were particularly pressed for time at all. Okay. So today and tomorrow, I want to complete the sort of siloed part, the sort of factual and conceptual download on the science part of the climate problem. And there's a lot of focus on the science part of this problem compared to some of the others. We'll have lectures on all of the others as well, but it's because although there would still be a food, water, and biodiversity problem without the climate problem, if there weren't any of the other problems associated with food, water, and biodiversity, the climate problem alone would create food, water, and biodiversity problems. So that in some sense, it's more integrated as a problem than some of the others. So today I want to talk about the link between fossil emissions and damaging impacts. How much can we afford to emit? And I've got a picture here of Hurricane Katrina, which a number of years ago slammed into New Orleans and caused trouble. And I've got that there to remind me that today is about the sort of average impacts of climate change. And there's a separate science which is about the extreme event impacts of climate change, like Hurricane Katrina. And this second field is really on the bleeding edge of the science. When I taught these lectures last year, the statement from the IPCC was still the last IPCC report was still the guiding statement for hurricanes in particular, and that is that it's impossible to attribute a hurricane to climate change. And in the intervening year, there have been a half a dozen explicit, scientifically credible, past peer review, came out in good journals by the best people, scientific papers attributing hurricanes in the past year. All right. And so all of these extreme events that have been outside the science are all storming in. And next time we'll talk about that because there are a number of interesting implications from our society, not the least of which is that when you've been damaged by an extreme event, you know what knocked your house down, killed your grandmother. And that turns out to give you legal standing. As a result, 900 separate lawsuits were filed last year in the United States alone about climate change damages to individuals and other entities like cities. So I want to talk about that next time, have a bit of a discussion about it. But this time is about the stuff that I would have been able to talk about before the last year. Okay. So again, here's we've seen the first two of these bars. This is the radiative forcing since 1750 of the extra CO2 we've put into the atmosphere, the extra methane we put in the atmosphere, and then I've got two other gases. These are fluorinated gases that are regulated. Some of them under the Montreal Protocol to fix the ozone hole, and some of them by some recent side agreements. They're long-lived but minor. And this is N2O. N2O is what happens. Most of the emissions of N2O come from fertilizer. Put a lot of fertilizer on the land, and some of it can go up into the air as N2O. So CO2 is the most important greenhouse gas today. And this graph down here has atmospheric lifetime in years. And it's a log scale, so that's 10, that's 100, and that's 1,000. And this is how much radiative forcing it has relative to an equal mass of CO2. So 1 means it's the same as CO2, 100 means it's 100 times more potent, kilogram per kilogram, and 10,000 means obviously 10,000 times more important. And CO2 here is by definition 1 on this radiative forcing scale because it's as potent as CO2 right now. It's the same thing. But notice the long lifetime. These other gases, I'll get back to this in a minute. Last time we talked briefly about methane, which has roughly a 10-year lifetime, over 100 times more radiatively active. And then some of these other compounds, these are the fluorinated compounds, are 10,000 times more active and they have somewhere shorter lifetimes than CO2. This blue dot here is so-called black carbon. That's a sooty-like stuff, and it has fantastically high radiative forcing. But it's extremely short-lived in the atmosphere, like hours, okay? So the deal with trying to manage the atmospheric greenhouse gas load is that you're constantly dealing with apples and oranges. Some things, if you stop emitting because they have short lifetimes, they go away immediately. The atmosphere just dumps them. Others you could stop emitting and the atmospheric concentration stays about the same. Global warming doesn't really decrease because they're so long-lived in the atmosphere. So let's talk about CO2 first of all. Because CO2 is long-lived in the atmosphere, because it stays there for a long, long time, stays there for so long that the slow to catch up climate, remember the slow warming of the oceans that can take a couple thousand years, that gets to catch up to the CO2 in the atmosphere because it stays in the atmosphere for such a long time. And so the cumulative CO2 that we've ever emitted is a really good gauge of how much total warming it's ultimately going to produce. Now this is a graph. There are different graphs like this that depend that differ in how they calculate this global mean temperature change. This is from the National Research Council, which is a wing of the National Academy of Sciences. And so we can expect them to be unbiased, all right? If you look at graphs like this from environmental pressure organizations, they'll often show an interaction that's a little different and a little more alarmist. And if you look at it from a fossil company, it might be the other way around, right? So this is sort of middle of the road. And what this shows is that these are cumulative emissions in terms of billions of metric tons of CO2. This is the estimated to date. And this is a couple of years old, but not that many. And you see we're just at about 1 degree Celsius, which is consistent with the warming that we've seen. And 2 degrees, which is the Paris Agreement, means that that's how much we have left. And the nice way to think about this is that it's a budget. There's a finite amount. If we're going to stay underneath 2 degrees, there's a finite chunk that we're ever going to be able to emit. That's it. If you emit it today, you can't emit it tomorrow, that sort of thing. And that then asks interesting ethical questions about how you want to apportion that remaining pie. The Bolivian envoy during several of the Paris talks always calls this the atmospheric pizza. And she always says that you've eaten the pizza. You people have all eaten a pizza and you're leaving us the crust. Okay. So anyway, so you see that this is approximately linear, right? And so the system, in a sense, is pretty simple. We've emitted at least, according to this, about half the CO2 that we could emit and still get to the Paris Agreement. But of course, we're emitting at a much higher than historical rate, so it won't take very many years to get there. If you look at other publications, they'll say, nah, we're closer to 2/3. We only have half again as much to go. Okay? All right, now this is only an approximation though, because of natural carbon sinks. Natural carbon sinks actually complicate this picture. This would be true if dumping CO2 in the atmosphere, if it just stayed in the atmosphere and that was that. But that's not quite what happens. There are these carbon sinks. Now, this graph, although ugly, I should make a prettier version. I actually haven't found a prettier version that is prettier. And this is from the same National Academy report. And these are just hypothetical curves, but it shows, if you can assimilate this, you'll have a clear idea of what's going on. Because I can't tell you the number of people that are confused about this. In Congress, when I talk to people, Congress people and senators, they're always confused about this. I mean, almost never not confused about this. So here's a hypothetical emissions curve of increasing emissions going into the future. You might think of this as a business as usual emissions curve. All right, and this is gigatons of carbon, not gigatons of CO2. Remember, you have to remember the conversion. This is what would happen if we had stable emissions. As we'll see in a couple of times, the Earth has had close to stable emissions over the last few years. All right? That would be stabilizing emissions. No more growth in emissions. And this is what we talk about as an emissions trajectory consistent with the Paris Agreement for developed nations like ours. So Obama's targets were an 80% reduction in emissions 3 times, and at least a 50% reduction by around mid-century. Okay? So these are 3 different trajectories. Growing business as normal, stabilizing emissions, or crashing emissions. Now let's see what happens to concentrations. In the first case, concentrations go up. With stable emissions, concentrations go up. Concentrations go up because the CO2 stays in the atmosphere forever. So even if you're emitting at a constant rate, all the CO2 that you've already put in there is still sitting in there, and now you're putting some more in. And then the next year you put some more in, and then the next year you put some more in, so it just keeps going up and up and up and up. Stabilizing emissions is not the same thing as stabilizing concentrations, and that's what keeps all of your lawmakers, elected officials, confused. To get a stable concentration, you have to have steeply declining emissions. That's the critical story. You have to have steeply declining emissions just to stabilize the concentration. And once you have stabilized the concentration, you have not eliminated global warming. You've stabilized the growth in global warming at the worst it's ever been, okay? So that's what we say as that's the solution to the problem. Stopping the growth of global warming damages, other than those that are baked into the system from the slow equilibration of the oceans with atmospheric CO2. To actually cause global warming to decline, you'd have to have this concentration actually fall. And that would require a lot of interesting stuff that we won't get to till the very end. Most of the literature about that is on so-called negative emissions technologies that would pull CO2 out of the atmosphere and put it into the ground. You can think of it as a terraforming technology for the Earth. Okay? That's really what it is, right? It's a planetary engineering technology. Now, emissions do not need to stop altogether to achieve a stable concentration, the way they would if this were a simple system, because of natural CO2 sinks. You see, if there were no natural CO2 sinks, so all the CO2 you put in the atmosphere stayed in the atmosphere forever, then to stop the growth of atmospheric CO2, you'd have to stop emitting altogether, because everything you put in there stayed in there, and it would just bump it up again, right? And because you don't need to do that to stabilize concentrations, the reason is because of natural CO2 sinks. So we need to understand natural CO2 sinks because, to a very strong approximation, if the Paris Agreement is adhered to, the size of the fossil economy is going to be dictated by the sizes of those sinks. Now, what are these sinks? So, this is a thing called the Global Carbon Project. That is, the principal on it is a woman who used to work here as a postdoc named Corinne Le Carre in an institute in Paris. And every year, she and her team review what the carbon cycle was done in the last year. And this is the review for the period of 2006 to 2015, published in 2016. There's just been a 2017 version released, and I have some of those figures in the rest of this talk and elsewhere. Now, for that decade, 2006 to 2015, there were 34.1 gigatons of CO2 released from fossil fuels, all right, globally. 34 billion metric tons of CO2. Remember to divide by about 8 to get ppm, and that would be something like 4 parts per million worth, okay? 34 divided by 8. 9% of the total was actually produced because of cutting down, net cutting of tropical rainforests, where the trees that are mostly made of carbon decompose and go into the atmosphere. And so it's about 90-some% fossil and 9% deforestation, and then there's a little bit from cement production that we're ignoring. Now, what's interesting is that of this 37.6 gigatons of CO2 that humans emitted to the atmosphere, only 44% of it actually showed up in the atmosphere. The rest of the 56% never bothered to show up in the atmosphere. Good news, all right? What kept it from the atmosphere? Well, 31% of the total went into fattening the terrestrial biosphere. We'll talk about the mechanisms of that. There are a couple, but the biosphere, the terrestrial biosphere in particular, is gaining carbon. All right, when you as a human gain weight, as long as it's not water weight, you're gaining carbon weight, right? Same thing's happening to the terrestrial biosphere. It's getting fatter and fatter. And it's keeping a lot of the CO2 we emit out of the atmosphere. The remaining 26% goes into the oceans with a couple of different mechanisms. So this is like fantastic. This is like nature decided, I'm going to take up more than half the CO2 you release and keep you from damaging yourselves as much as you otherwise would. And as a result, the atmospheric concentration didn't go up 4 parts per million per year over this period. It went up at less than half that. All right. So this is like a free ecosystem service. What a good deal. And it's why I said last time that currently the carbon cycle feedbacks in the natural world are negative, that is, regulating feedbacks. If they were positive feedbacks, these two things would be emitting CO2, not taking it up. So as we emit CO2, they continue to take it up. Now, this is also important because these are the two money parts of the Paris Agreement. Article 2 says that we're going to have significantly less than 2 degrees C of warming, with an aspiration for 1.5. But the only number that's really enshrined as a target that's agreed upon right now is 2 degrees. Everything else is talked about in aspirational terms. And of course, 2 degrees is still aspirational, right? Article 4, Section 1 says that sources should balance sinks after 2050. What it really says is to achieve a balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases in the second half of this century. The thing is, though, that if you're going to achieve 2 degrees, the only realistic way to do it is to have sources balance sinks by 2050. So that there are no net new emissions to the atmosphere starting in 2050, all right? And so 32 years hence, right? Which is almost exactly, in preposterous geek terms, 1 billion seconds, all right? So that's the countdown here in your lives. It starts almost now, and every second that goes by is one of the billion that you don't have when you first heard this, okay? 1 billion seconds is, yeah. So 1 billion second birthdays are good to actually have in your life, you know, because you only get, well, you may get none, right? Most people get 2, and getting 3 is like a really good deal, right? So, but you'll never get 4. All right. All right. So you can figure out how many 1 billion seconds is. You actually, and do it right? Don't screw around with it, just actually do it right. Because you want to actually have it marked on your calendar. You know. So pull out your clickers. This is sort of a throwaway, but I actually want to see what you people think. Because 32 years, 1 billion seconds, that's like harsh, right? It's like stopping emitting emissions in 32 years. It's so harsh. So what's the most likely path, do you think? Is it, well, these things. U.S. leadership doesn't look so good lately. Chinese leadership, they really have stepped up. You got to hand it to them. Disruptive new energy technology. or global economic depression. I think. Which, that would work. I mean, there are others, like, nuclear war. All right, so this isn't that serious, so get finished. You guys are finished. No. Oh, look at that. It's a new record. I'm quitting this thing. So C, disruptive new energy technology. You guys are technological optimists. I love that. Okay. This is true of academic audiences and sort of the more elite the institution, the more that answer is the one that everybody loves. All right. If you go to the general public, they're like, "Yeah, we'll never do that," and so they think it's economic depression. It's the only possibility, right? But I agree with you. I think that this is a problem where if we achieve it, it's going to be because of some technological fix. And we won't get to this till the end of the course, but I think that of all of the Nexus problems, the greatest single beacon of optimism is in the absolutely unprecedented and glorious progress on new energy technologies in the last decade or so. Unprecedented in human history, all right? Really spectacular. Still a long way to go, but it's like every smart person is attacking it in this way, right? So many of the innovators who are good at that sort of thing, they're all doing that rather than doing something else, like working in financial services or something. And the problem is starting to crumble, right, to the sort of combined onslaught of human ingenuity. I love that. It's not going to save us. We still have all kinds of danger, but it is going to, it's going to, it's still fantastic if it works, right? It's going to be fun. Okay, so I have to start making some progress here, and this is not that I wish this is the wrong thing. All right, this is the carbon cycle, and I don't expect you to memorize these numbers. So I'm not going to have like a thing like this on the exam with the numbers missing and say put them in. All right, but do look at this. Watch this. Take a look and see what's going on here. So this is just a diagram of what was going on in the previous couple of slides back. These are geologic reservoirs, and this is the fossil stuff. It's coming out of geologic reservoirs. It's going into the atmosphere. The atmospheric growth rate is less than half that. Land use change, burning up the tropical rainforest is less than 10% of that. There's this great big land sink of 11.5 that's coming in and fattening the biosphere, and there's a smaller ocean sink that's going into the oceans, and that's the fundamental diagram. All right. 2 sources coming out, 2 sinks coming in. The sources are about double the sinks. And why are there these sinks? All right. Why are there these sinks that have solved more than half the problem for humanity over the years? And it's because of Le Chatelier's principle, but we'll talk about that in a minute. The dominant cause of the land sink, there were two causes, but there's superabundant evidence now that a big piece of it is so-called CO2 fertilization of plants. So plants eat carbon dioxide for a living. So this is photosynthesis. CO2, 6 of them, plus 6 water molecules, plus a bunch of sunlight energy, makes a glucose molecule and some oxygen. This is why we have oxygen in our atmosphere, right? It's because plants have been doing this for over 3 billion years. And this is the precursor of all the organic molecules that are made from glucose. And so the important point is, I don't know if you remember baby chemistry, or if you're a scientist, you remember, but you probably remember from high school or even junior high, that when you have a chemical reaction like this, if you put more stuff on one side, it causes more stuff on the other side, all right? And if you put more stuff on this side, it causes the back reaction to happen. That's called Le Chatelier's principle, okay? And it's this sort of principle of mass action that has a chemical reason for it. But you probably remember that. And so when you put CO2 into the atmosphere, the plants make more sugar, and the biosphere gets fat on the organic molecules that it's making, that's coming from the atmosphere. So that's the big cause. And there's a second contribution from reforestation. If in 1912, you had gotten in a primitive airplane and flown to Iowa and looked out the window, all right? And if you made it, you would have looked out the window and almost never seen trees. Less than 5% of the land surface would have been covered by forest. Now, most of you done that now. You've probably flown across the eastern US now. And when you look out the window, more than 3/4 of the time, when you look down, there's a forest. And all that forest has grown up because the agricultural land in the east was abandoned as people shifted to mechanized agriculture and found other things to do with their time. And those processes that cause land to be abandoned as people become wealthy and focus the agriculture on the most productive land are going on everywhere in the world. And so we're starting to see that same reforestation in a large fraction of the tropics now. So that's the other contribution. In the oceans, it's the same sort of thing. You can think of this Le Chatelier's principle. You can divide the ocean into a shallow ocean and a deep ocean, the abyss. Shallow, the first few hundred meters, and the deep ocean, the couple of miles below that. And the atmosphere is, of course, in contact with the surface, and the deep part of the ocean underneath that is in contact with that shallow ocean. And so there's CO2 is in equilibrium. It's going into the water, being dissolved, and also being incorporated into the microscopic plants that live in the ocean. And enriching the CO2 in the shallow ocean, which enriches it in the deep ocean. And so when you increase CO2 here, you increase CO2 here, and you cause CO2 to be injected into there, right? And so it's the same thing. It's Le Chatelier's principle. There is this complication of the so-called biological pump, which those of you in the ST sections will probably talk about the biological pump. The biological pump is fantastic and interesting. It's simply that phytoplankton, the little microscopic plants in the ocean, take up CO2, turn it into plant. And unlike on land, almost all plants lose their lives to an herbivore. Usually a herpetoid copepod that comes in and kills them within a few days, right? I mean, it's just like tough out there. That's why the ocean is so blue. Everything gets eaten, right? It would be green otherwise, right? And it turns out, because of a bizarre quirk of nature, copepod poop sinks. And so the poop sinks to the bottom of the sea and constantly pumps CO2 from the top of the ocean all the way down to the bottom. All right, and that so-called biological pump is also governed by the Chatelier's principle. All right. Now, these sinks have been going on for a long time. So there's a 50-year record of them that we have, that we can infer from measurements that have been taken. So this is the atmospheric growth. This is the growth in fossil emissions over 50 years. This is the contribution from deforestation over 50 years. It's been a flat, with some wiggles, emission. The land sink has slowly inched up through the years. These big wiggles are mostly due to El Nino events and burning, primarily in Southeast Asia, associated with an El Nino. The ocean sink has gone up steadily, and the atmospheric growth rate has gone up steadily. But for over 50 years, the concentration that ends up in the atmosphere has been about 45%. So it was 44 over the last decade. And that simply means that these sinks have kept pace with the growing emissions. They've always kept this same fraction. And that's kind of mysterious. In our explanations as scientists for that are that, it just worked out that way. All right, there's no a priori reason why it should be constant, but it is, right? So that leaves me uneasy, frankly, as a scientist, that we have models and we predict that, it should have been, but it just happened to work out that way. There's no more fundamental reason why it should have been about a 44% ending up in the atmosphere for 50 years, but that's the way it's been. So this is just one scenario for how much we could emit over the next 100 years if we were to stabilize atmospheric CO2 at a level that 442 ppm that would lead to a 2-degree warming and be consistent with Paris. And the interesting thing here is that this would be zero right here without the terrestrial and oceanic sinks. In other words, that emission over that period is exactly equal to the fossil plus land use emission. All right, that fossil plus land use emission is exactly equal to the strength of the natural land and ocean sinks over that period. So there's zero net emissions over this period inside the box because those natural sinks are taking up all of the fossil plus land use emissions. All right? And here we continue. We see here's where we are now, and this scenario says that's going to have to drop down to this level where the atmospheric concentration will no longer increase because the natural sinks are taking up all the humidity. And that's what I mean when I say the Paris Agreement is consistent with the view that in 1 billion seconds, the size of the fossil economy is going to be dictated by the longevity of the natural sinks. Right. That's the money statement. The reason this wiggles around is this is just one run of the Earth system model that we have here at Princeton. I don't know if you know this, but the place where climate models was invented was here. There's a NOAA laboratory that builds the guts of climate models here, has done for over 50 years. It's located on the Forrestal campus, 100 PhDs. All they do is that. All right. And so this is their model. This is one run. It wiggles around because there's El Niños and La Niñas and all kinds of crazy stuff going on in the model like that. Okay, so let's talk a little bit about methane. Methane's the second most important greenhouse gas. And remember, it's got higher radiative forcing, but a smaller atmospheric lifetime. These are the sources of methane. Fossil is at most 1/3 of the total, and the rest is all biogenic. The stuff from biomass burning and biofuels production is a small part of the total. That is mitigatable, though. There's stuff you can do for that. Domestic ruminants, the cattle and goats and sheep of the world are constantly belching methane. And they do so because they have anaerobic flora in their rumens and their digestive organs that produce methane. And they're responsible for as much as leaks out of fossil fuel. Why does it leak out of fossil fuel, I should say? Natural gas, the fuel natural gas, is almost entirely methane. And that means whenever natural gas escapes from a pipe or from a well or from incomplete combustion in your home water heater or furnace and goes up into the atmosphere, that's an emission of methane to the atmosphere. So natural gas is itself a potent greenhouse gas. There's a fair amount from rice cultivation. If you change the way you cultivate rice, it's possible to shut down most of that. And there's a fair amount of waste decomposition from landfills, which it's possible to catch and actually use again. So there's a lot that can be done with methane. An important debate that has gone on in recent years, especially if you live someplace close to a fracking site, is the fracking debate. And fracking is the process of drilling into shale and then drilling horizontally and pumping water with a bunch of stuff in it at super high pressures in there and cracking the rock, which causes natural gas that had been bound up, absorbed to the shale rock to come into that fracked zone and then come up the pipe. And so it has made, fracked oil and gas has made the U.S. close to the dominant energy producer in the world when we were about tapped, and it has made natural gas super abundant and really cheap. But it's also freaked everyone out because, you know, they're drilling under your house and cracking all the rocks and stuff like that, right? And with good reason. So there's a big debate over it. And part of that debate says, well, is gas really better than coal? So the argument that gas is better than coal is that gas combustion emits half the CO2 emissions as coal per unit of energy produced. So you can produce the same amount of electricity with half the fossil emissions. So you'd say, well, that's great. It's like getting rid of half the coal plants. And that's true. The reason, incidentally, is that because CH4 has so many hydrogens per carbon, most of the energy when you burn methane actually comes from burning hydrogen, which just makes water vapor. Only a little bit of it actually comes from the oxidation of the carbon itself. And so that's why it's all those hydrogens that make gas a cleaner fuel. But the problem is if even a little bit of that gas leaks out of the pipe before it gets to the electrical power plant, then it's such a potent greenhouse gas, 120 times more potent than CO2, that it can negate that advantage, right? Because it's so big a deal. But how does one compare the emissions of CO2 and CH4 anyway? To answer this question, should I be for gas as a bridge fuel because it's better than coal or not, right? And the answer is not if the CH4 is leaking out, but yes if it isn't. But then how much can we afford to have leak out? And there's this complicated answer to the question that I debated taking out of here. I'm going to try again. I tried last time and it was largely unsuccessful. So I'm going to give it a try here. So what happens when you emit a kilogram of CO2? Well, it's this little dashed blue curve here. Because the CO2's, most of it that ends up in the atmosphere, the 45% or 44% that ends up in the atmosphere, then stays there. The total radiative forcing from that kilogram of CO2 stays the same for a long, long time. See, that's out to 120 years. If we take the same mass unit, a kilogram of methane, and emit it to the atmosphere, immediately, because it's so much more radiatively potent, it's 120 times worse than CO2. See that? But because the methane has a 10-year half-life, it decays out of the atmosphere as it's oxidized to CO2 by photochemical processes and other things. And so its radiative forcing at any one time constantly decreases. And so if you want to say, well, how much global warming does the methane cause relative to the CO2? And the answer is, well, you do that by adding up the total amount of warming, which is the area under this curve, up to some time horizon. Okay? And that's the cumulative radiative forcing of that emission. And it's sort of how much heat you put into the planet. Remember, mostly going into the oceans, which are slowly equilibrating. All right, so if you integrate out, that is, calculate the area for the cumulative radiative forcing for methane, and do the same for CO2, and divide one by the other, you get this thing called a global warming potential, a GWP. And this is what is talked about in the literature, and it's enshrined in laws, and there's all this stuff that's used to compare two different greenhouse gases. Now, the problem is that this measure, which is again the area under the light blue curve, up to some time horizon, divided by the area under the dashed curve, which is just at 1, up to some time horizon. The measure depends on the time horizon. What is the limit? Between 0 and TH years out, time horizon years out. So if it's 10 years out, the global warming potential here is something like 90. If it's 100 years out, it's in the 30s. And the two values that are used commonly are 20 years and 100 years. And the global warming potentials in the last IPCC report are 86 for 20 years and 34 for 100 years. The important thing to know is that there is no scientifically correct time horizon. The choice of a single time horizon is made for two reasons. The first is sales. Somebody's trying to sell you something and they want to make gas look better or worse. And the second is ethics. Whether or not you care more about damages near term or long term. Okay? And so we're going to get to that later on in the course. But this choice of a time horizon is not scientifically justified. A scientist wants at minimum two values from which they could reconstruct the curve, okay? And ideally wants the whole curve. So I have a question here. You can read it. If you were an anti-fracking activist, you wanted to stop gas production, which time horizon would you choose to argue that gas is as bad or worse than coal? Okay. And finish up quick, because I'm behind. Like I'm totally behind. But I'll.
Okay, last couple. Push the button, push the button. 5, 4, 3. You're done.
All right, so we got 0 years, 10 years, and so who said 0 years? Somebody who said 0 years. Can you tell us why you said it? Come on, don't be shy.
I said 0 years because the immediate effect of years bias.
Yeah, that's exactly right. I mean, it's not, this is not a hard question, right? I just want to make sure you're paying attention, and almost all the class was, right? So the point is that because the global warming potential, the effect of methane on the climate relative to equal mass emitted of CO2, because that starts high and then gets low. If you want to show that gas is bad for the environment, you want to choose the highest possible value you can, which is the shortest possible time. All right, so the bottom line is that since there are 2 global warming potentials that are used all the time, one for 20 years and one for 100, anti-fracking activists and environmental NGOs almost always use 20 years, and the fossil companies almost always use 100, all right? And what we really should do is treat them like, say, blood pressure, and always report 2 numbers. Right, systolic and diastolic, or highway and city mileage for a car, right? Because they're really different. We should actually have 2 and expose the ethical trade-off between short-term and long-term damages, all right? That is inherent in choosing one fuel over another, right? That's the critical thing here. All right. Maybe this thing will work. Oh, there's something happening. There we go. This thing is. There we go. All right, so CO2 equivalent. CO2 equivalent means the CO2 concentration plus the concentration of other greenhouse gases, each converted into the CO2 concentration that would have caused the equivalent reading of 4 to 6. You'll see this all over the place in readings and in graphs for the rest of the course. It'll say CO2 peak. And what that means is this is not just CO2, it's the other greenhouse gases converted into an equivalent CO2 concentration. But as we've just seen, when you do that, you have to assume a time horizon. So there's always a lurking time horizon in there that is not explicitly stated. So keep your eye open for it. Mostly, if it's in the scientific literature, it's 100 years. But there is no scientifically sound reason why it ought to be 100 years. It's just because it's 100 and we happen to have 10 fingers. Okay, so climate change, that's right, it's power 2 over 10, right? I mean, it literally is an artifact of having 10 fingers. Okay, so climate change impacts. There is superabundant evidence about the impact of climate change on the weather. And I've listed some of them here. I'm going to go through some of these, but I'm also going to ask you to go through the slides because I'm going to run out of time, and because these impacts are all pretty easy to read off of the slides. And also because these images are, at least in this lecture, disembodied from impacts, from harms on people. And so they're actually hard to put into context, right? And so I'm not going to ask you details about, for instance, this figure. These are the different RCP scenarios that we talked about. This is the one that's consistent with aspirational Paris, the aspirational parts of the Paris Agreement. This one is possibly consistent with the Paris Agreement. This is the temperature at the end of the century. if you're emitting along these different trajectories. And you can simply see that it's getting warming. And the interesting thing is that the Arctic, you see, and the land areas get warmer faster than the poles. These numbers get quite large. As we'll see later in the course, this scenario would put alligators in Carnegie Lake. All right. It would make this place look very different. This is an impact of climate change on extinctions, and it's actually an interesting phenomenon here. Turns out that a lot of species have thermal and other climatic limits to their species ranges. They can't live if the climate gets too hot, all right, or too cold. And when the planet's climate changes, the thermal boundaries of the species range start to move across the planet. Like, for instance, in the US, the warm boundaries are moving north as the north gets warmer. And so those boundaries will push species ahead of them that can't tolerate the warm temperatures. And the question is, under global warming, how fast do those fronts move relative to the capacity of species to move? And so these show velocities of species. The blacks are medians from data. And the lines show different speeds for different warming scenarios. And you can see that the business as usual ones here, RCP 8.5 and RCP 6.0, move faster than a lot of species could move. So this is one of the reasons why we think that climate change, which is happening much faster than in the past, could overwhelm existing species and cause significant extinctions. Species won't be able to keep up, in a sense, with the moving climate. There is a tendency, this is winter and summer, for dry areas, which are in the red, to get even drier, which is what the red means, and for wet areas like the far north to get even wetter, so that there will be a change in water availability. There is already tremendous coastal flooding. 67% of the coastal floods since 1950 were caused by the sea level rise to date. This is the amount of sea level rise that we expect under 2 degrees C of warming at equilibrium. This is the bull outside of Wall Street, and this is with 4 degrees C of warming. Just a little bit of the bull there left. And the little girl is submerged. Okay. This is what happens if you lose an ice sheet. We lost the Greenland ice sheet. Seas go up 7 meters, 60 meters with the East Antarctic ice sheet, 5 meters with the West Antarctic ice sheet. Not likely this century if Paris Agreement, but if the Paris Agreement is implemented. But those numbers, the expected sea level rise is going up all the time and looking more and more dangerous through time. We expect big decreases in crop yields, particularly in the tropics, Indian wheat and African maize. This is the amount of yield change. Negative means declines as a function of different amounts of warming. Decreases in the primary oceans that fuels our fisheries. Blue means expected decreases in the primary productivity of the oceans, although some places will see increases. Changes in the distribution of diseases. This is the projected area for one of the common forms of malaria under a mid-century climate change. And you can see that the United States is crawling into this, to the range of this tropical area. Increased wildfire risk because of warming. This goes up really fast. That number is 470%, a quintupling. And in fact, as we'll see next time, the attribution of wildfires is now, wildfires we see now are in fact caused by global warming today. This is a list of extreme weather predicted and the likelihood under the IPCC AR5. I'm going to give an entire lecture on this tomorrow, or day after tomorrow. But it's supposed to be 70 degrees out, which is great, right? And then this we've talked about before, the cessation of the thermal haline circulation. All right, if deep sea circulation of the ocean stops, and that's not expected under current warming. I'll finish the rest of this next time. We're out of time. I've only got a couple of slides left.
Thank you.